Hello dear students, welcome you all. In this lecture, I am going to discuss about the Fermi gas model of a atomic nucleus. You know very well that in the previous lecture, I have discussed about the first nuclear model, that was liquid drop model, right? That was based upon a semi-empirical mass formula. In the previous lecture also, I have explained about the benefits of liquid drop model, drawbacks of the liquid drop model, and I told you that there was a new need of a new type of model that can explain many features which was not explained by the liquid drop model, right? So the Fermi gas model was the next step in the process of explaining all the properties of atomic nucleus. So as it is evident from the this title, Fermi gas model, so obviously this model is based upon the Fermi-Dirac statistics, right? And you might have remembered that in the quantum statistics, I have discussed about the Fermi-Dirac statistics, and in that statistics we have an article that is free electron gas, right? This approach has been used to explain various properties of the atomic electron by treating them equivalent to the gas molecules of a gas contained inside a container. So in that article we have named these electrons as a free electron gas. So now we are applying the same analogy here in the nuclear physics. In the nuclear physics, we are extending this free electron gas model to the free nucleon gas model now. Now the model will become free nucleon. Nucleon means either neutron or proton gas model. So now you might have got the picture clear that here in this model we are going to consider both neutron and proton inside the nucleus as free gas of nucleon. Free gas means they are totally independent of moving inside the nucleus, within the boundaries of the nucleus, right? But they are unable to come out of the nucleus because of the potential barrier, just like the movement of the gas molecules inside a container, right? Now before proceeding further, I'm going to take up the assumptions that were made in this model. So the first assumption is that this model is based upon a Fermi-Dirac statistics that I told you already. This is the first model, first assumption, sorry. Now in this model we have assumed both neutron and proton as free particles moving inside the nucleus. Right? We know very well that both neutron and protons are fermions. They have a half integral spin. So they obviously obey the Pauli's exclusion principle, right? So this is the third assumption. They obey Pauli's exclusion principle, right? Now the next is the potential. Now the next assumption is very important. According to this, both neutron and proton, they have their own potential various potential wells, right? We know very well because they have both have different properties, like the protons have charge but the neutron don't have charge. So proton repel each other, right? But neutron don't repel each other. They only attract each other because of the nuclear force. So obviously they will have a different potential wells in which these are present inside the nucleus. So both neutron and proton have a separate, or we can say, no, I will not use the separate, but different different potential wells. Different potential wells means the height of the potential well will be different in both the cases of neutron and proton, right? The next assumption is both neutrons and protons are filled in these potential wells in the different energy levels, but up to a certain energy level that we call as a Fermi energy level. And it is very important that both neutron and proton, right? Both neutron and proton have a same EF. The Fermi level for both of them is same. We know very well what is the Fermi energy and Fermi energy level. Here, I want to make it clear that they have same Fermi energy level, the level up to which these neutrons and protons are filled inside the atomic nucleus, right, in separate bells. Because if they have different Fermi level, right, there will be an immediate possibility of the movement of neutron or proton, toward the different side, and we will get either alpha decay or a beta decay. In that case, either beta positive decay or beta negative decay, right? So these are some assumptions we have to take into consideration and keep in mind by proceeding further. Now I am showing you the potential well. You can see here the potential well, right? So as I told you that the both neutron and proton, right? This is neutron, right? And this is a proton, right? Proton potential well, and this is the neutron potential well. Now you can see the neutron potential well is deeper than the proton potential well. Why it is there? We know very well in the heavy nuclei the number of neutrons are more than number of protons. This is one thing. Other thing is proton repel each other, so they are adding positive energy to the net potential, right? So that when the positive energy or positive potential is added to the net potential, obviously its depth is decreased. It is not deeper than this one, right? It is up to this point. The proton potential well is up to this point, whereas the neutron potential well is up to this point. But both of them are filled only up to this level. This is the called Fermi energy level in both the cases, EF, right? You can see here. This is EF for neutron, EF for proton, but the height, the level height is same in both the cases, right? So this is the potential well, nuclear potential well. I will come to this at the later stage of this lecture, how it is calculated, right? Now, if I want to take this neutron or proton out of the atomic nucleus, right? We know very well, then we have to supply the energy, and we call that energy as a binding energy per nucleon or average binding energy, right? We have also seen in the first unit that where we have discussed the binding energy per nucleon graph and all other things, that its average value is nearly equal to 8 mega electron volt in the stability region, right? So it means if I want to get these neutron or proton out of the atomic nucleus or out of the potential well, then the this much of energy, this is the height, this one, right? This one. Now up to this point, right, this is the last range of this potential well. If I want to take the neutron or proton out from here, topmost field energy level, then I have to supply this 8 mega electron volt of energy. It means this height is a 8 mega electron volt, right? And if this total depth is 40 mega electron volt as it is taken here, then in that case it will become 32, right? But in this case this will become how much? This is 8 and this is then 32 in this case. But in this case, if it is 32, then it can't be 32 because it is deeper than this, right? So it is slightly less than 32. It can be 25 or 26 because we have additional depth here, right? I will explain it at the later stage of this lecture. But the thing is clear that the potential well of both neutron and proton are different. Their depth is different because of the two factors, right? Now I am coming to the Fermi energy. We know very well what is Fermi energy. All these things has been discussed in details in statistical physics, and when we have discussed particularly about the Fermi-Dirac statistics, right? and at that time we have derived the expression for the Fermi-Dirac distribution function, and that was given as I represent that Fermi-Dirac distribution function as if you want to go to those lectures, you can go to my lectures on the course statistical and thermal physics. There you can find the expression for the Fermi energy and all the details related to the Fermi energy, right? So I was talking about the Fermi-Dirac distribution function. So I'm going to write it 1 upon e raised to power e minus ef upon k, k is Boltzmann constant, plus this is Fermi-Dirac distribution function. Now let me make it once again clear that when the nucleus is in the ground state, then the filling of neutron and protons, as I told you that both neutron and proton fill differently. They have different potential wells, and they have different quantum states. So you can see here only two nucleon can enter in a given state, but they will have opposite spins. You can see here this one and this one, this one and this one, right, due to Pauli's exclusion principle. So the filling of the neutron and proton, you can see here now, starting from the lowest state in this case, right, opposite spins. So they will be filled starting from the lowest state, then the above and then we will have a topmost filled level, right? You can say that we call as a Fermi energy level at 0 Kelvin, because at 0 Kelvin we will have a that configuration in which all the energy levels up to a certain levels are fully filled and all the levels above that level are fully empty. Now I told you that in both neutron and proton they will have same Fermi level. Why? Because if the Fermi level of proton is higher, I mean if proton is present here, right, you can see here, then in that case this level is at the lower side, then there is a possibility then proton can go down toward this side by this reaction. Proton convert into neutron plus electron plus anti-neutrino, that we call as a beta negative decay, right? Sorry, positron. I wrong. Proton convert into neutron plus positron plus a neutrino associated with electron. Sorry for it. Neutrino associated. So in beta positive decay. So in this case, proton will go down toward this side, and if the number of neutrons are higher, the neutron side is higher. I mean, if neutron is present here on this side, right? Fermi level is here, then there is a possibility then neutron can come down toward this side. So in that case, neutron will convert into proton plus electron plus anti-neutrino associated with electron. We call it as a beta negative decay. So there is always a possibility. So to avoid this possibility, we are considering that both these levels are same. In both the cases, this level is the same, that we call as a Fermi energy level, right? We know very well that at 0 Kelvin, if I apply the condition of 0 Kelvin here, then at 0 Kelvin, all the levels E greater than EF, right? This function, Fermi-Dirac function, will become 0, right? If I have T is equal to 0 Kelvin, right, and E greater than EF, then it is a 0. Means all the now what is Fermi-Dirac distribution function is telling us? Number of the field energy states, right, with respect to the number of allowed energy states. But at 0 Kelvin, all the energy states above this are this function is 0, means no field state is there. But if I take E less than EF, then I have Fe is equal to 1, right? So it means all the energy states that are below EF, they are fully filled, right? So this is about the, once again I repeated the concept of Fermi energy and this Fermi Dirac distribution function. Now we have calculated the expression for Fermi energy in that article, and EF is equal to h cut square upon 2m into 3n pi square upon b power 2 by 3. This was the expression, right? Here m was the mass of electron, so I have to replace the mass of electron with the mass of nucleons. So capital M, right? V is what? Volume in which that system was there in case of free electron gas. So here what will be the B? B will be the volume of nucleus. So it will become 4 by 3 pi r cube. So it is 4 by 3 pi r is equal to r naught cube a, right? Because r is equal to r naught a power 1 by 3. So it is going to become it. So we can put all these values here. Let this is equation number 1, right? So now I can write this equation further. EF is equal to h cut square upon 2m into 3 pi square n upon b, right? Now b has been calculated as this, but I am going to put its value later. Now n upon v, what is power 2 by 3? What is n upon v? N upon B, we know very well in case of free electron gas, it was the concentration of free electrons, number of free electrons per unit volume. So in this case, it will be the number of protons and number of neutrons per unit volume. So if I calculate the number of protons per unit volume, right? NP, I'm writing it as NP, then it will be N upon V, right? We know very well the number of protons is equal to Z, right? So it will become Z upon B. So if I put the value of B, what it will become? 3Z upon 4 pi r naught cube A. What I did, I put the value here, right? So this is the concentration of we can say, or density of the free protons, right? Similarly, I can calculate the density of a neutron, Nn, that is equal to now number of neutrons, right? So number of neutrons is equal to A minus Z upon V. So I will get what? A minus Z upon B, then put the value of V. So I will get 3 times A minus Z divided by, again same thing, 4 pi r naught cube A, right? So this is the density of free neutron inside the nucleus, I mean N upon V, right? Now I got these two equations. Now in these two equations, let's assume R naught is equal to, we know very well, 1.2 Fermi, right? And also assume Z is equal to A by 2, special case when Z is equal to A by 2. So if Z is equal to A by 2, the number of neutron obviously equal to A by 2. So if I put here Z is equal to A by 2 and here A minus Z, obviously A by 2, it will become A by 2. So then these equations will modified according to it. NP will be 3 into Z means A by 2 divided by 4 by pi r naught cube A. So I got cancelled. So 3 by 8 pi r naught cube, right? So what I have to do, I have to put the value of r naught and pi here. So then when I calculated it, it will be 0.069 into 10 raised to power 45 nucleon per meter cube, because it is the number of nucleon per unit volume. So we have put the value of r naught, 3 upon 8 pi and r naught cube. R naught obviously 10 raised to power minus 15, right? 1.2 Fermi. So it when it will go upside, it will become positive 10 raised to power 45, right? Similarly, when you calculated the number density of the neutron, right, then it will become again the same thing, because here what you will get, A minus Z, that will be A by 2. So A cancel, and 3 by 8, the same thing you will get. So again, in the case of neutron, you will get the same thing, that is 0.069 into 10 raised to power 45 neutron or nucleon, we can say, or we can say neutron specifically per meter cube, and here it is protons. Now what I have to do, I have to put this value here in this equation, then I can find out the Fermi energy, right? So Fermi energy expression was EF is equal to h cut square upon 2m into 3 pi square into n, either p or n, right? You can take whatever value you want, power 2 by 3, right? So we have to put the value of either np or nn from here in this equation, that it is equation number 2. So when you will put this value in equation number 2, you will get the value of the energy around 33 mega electron volt. So the important thing that we found here, that in both the cases for neutron and proton, I calculated the value of the Fermi energy and it is same, 33 mega electron volt. But here I have made an approximation that the nucleus contain Z is equal to A by 2. So if I take it slightly different, Z not equal to A by 2, even then I will find this value nearly equal. I mean, for the one particle neutron, I will find 34 mega electron volt. Then the other for the second particle, I will find 33.76, something like that. So the Fermi energy will be nearly same, right? That's why you can see here I have told you that the Fermi energy in both the cases is same, right? And now this Fermi energy from the this here, it is equal to 33 mega electron volt. We have calculated it. So this was 8. So 33 plus 8, it is 41. They have taken it 40, but it is around 40. So we can say it is 40 or 41 mega electron volt, right? So 33 plus 8. 8 is same for both, right? But here now the depth of this potential well, right, from here to here, it is not actually the 33, right? It will be, as I told you, around 26 to 27 for protons, right? 26 or 27 mega electron volt, and the rest 6 to 7 mega electron volt will be this depth, right? This is this depth is more in the case of neutron, right? So this is about the Fermi energy for both neutron and proton. So we have explained it. So now I am coming to the applications of this Fermi gas model. Applications. So you can see here, as far as the applications, the very first thing is that we are able to calculate the depth of the potential barrier of nucleus, right? In both for both neutron as well as for proton. This is the big success of this model. The other thing is this model is able to predict the possibility of beta negative or beta positive decay here, right? If the either neutron or proton go to the excited states, I mean to that states which is just above the Fermi level, you can see here these will be the excited states, energy levels. If so neutron and proton are present in any of these excited states, there is possibility then they can undergo the beta decay, either beta negative or beta positive. So these are some features. It also explain this Fermi gas model also explain the possibility of alpha decay and other associated properties in the radioactive decay, but it was not able to fully explain or understand the concept of this radioactive decay, right? Although it makes some rough predictions, as I told you, but still it was considered as a modification of the liquid drop model due to these some successes. And but if we look at the side of the failures, then again this model is silent on many properties of the atomic nucleus. If I talk about the magnetic dipole moments, spin, spin angular momentum, right, parity of the nucleus, magic numbers of the nucleus, all these things were not explained by this model. It is totally silent on that issue. So due to this, this model was later on replaced by another model that we are going to discuss in the coming lectures, right? So thank you very much.